Welcome to this lesson video. Today's lesson is about work, energy and power. Now we need to understand what is work, energy and power. In this lesson video we'll be looking at the basics. We explain some of the concepts so that you become familiar with the terms and the equation used in this chapter. This is lesson 1 of this chapter. Just make sure you go through this lesson, and then from here, when you're done with this lesson video, you go to the next lesson video based on this chapter, which is lesson video number 2, where we look at question papers so that you won't be confused when we use certain equations and terms to answer questions from the question papers. Now let us start with the basics. What is important is to know the equations, is to know the definitions and the laws. Now you can see that this chapter is classified into 3 different types of subchapters or subtopics. Now we are going to talk about work, we are going to talk about energy, and we are going to talk about power. Now let us start with work. What is work? Well, work is some type of an energy because the SI unit is joules. So when you talk about work, suppose we have an object. Then this object is experiencing a certain force, might be a force applied or any other force this direction. And then somehow the movement or the motion of the object is this direction. So we can see that this is the force, this is the displacement of this object. Now whenever an object experiences a force and that particular force is parallel to the displacement of the object, we are saying that force is doing work to the object. Now let us explain this further. Let's say we have this object. This object experiences different types of forces. Let's see this force. We say this is force applied, and then we have kinetic friction, K. We have our normal force, and then lastly we have force of gravity. Now focusing on the motion of the object, let's say the direction of the object is this direction. Actually the proper term is displacement of this object is this direction. That is our change in x. Actually let me write it here. So between all these forces, which one does work on the object? Now we said in order for the force to do work on the object, it must be parallel to the displacement. Now we look at kinetic friction. We can see that kinetic friction is parallel to the displacement. So kinetic friction is one of those forces which does work on the object. Now we look at the normal force. You can see that the normal force is perpendicular to the displacement of the object, so there is no work normal force doesn't do any work on the object. Now let us look at other forces which does work. We can see that force applied is parallel to the displacement, so work is done by force applied. Now the last force, which is force of gravity, there's no work done because it's perpendicular to the displacement. So in simple terms, this is how we define work. Now there are equations, or there's an equation which we can prove that normal force and force of gravity in this particular scenario, whereby the object is on top of a flat surface, work is not done by these two forces. Now there is an equation to calculate work. Now work is defined by this equation. W is work, force multiplied by displacement multiplied by cos theta. This is work, this is our force, this is our displacement. Now this angle is the angle between our force and the displacement. I hope you can see this equation. Now let us try to explain this equation. A certain force experienced by an object the displacement of the object this is our force. Now to calculate work, we need the displacement. Since the equation is like this, now in this case, for us to calculate the work done by the force onto this object, we need the force, we need the displacement, and we need the angle between the force and displacement. Now since this force is on the same direction as the displacement, our angle will be 0. Let's say the very same displacement, we orientate it in this position. You can see that between the force and the displacement there's no angle. Actually the magnitude of the angle is 0 degrees. Let us look at Fk. This is our kinetic friction. The object is moving this direction. Kinetic friction is this direction. Now looking at the angle between the kinetic friction and the displacement, you can see that we have 180. So the angle of kinetic friction and the displacement, it's what? It's 180 degrees. I hope you can see this. Now let us explain this furthermore. We are trying to prove that normal force and force of gravity, there's no work done by these forces. Let us look at the angle between the displacement and the normal force. This angle is 90 degrees. Now what happens if we put 90 degrees here? We know that cos 90 is equals to 0. So this will be 0. 0 multiplied by this, everything becomes 0. Then it means work will be equals to 0 joules. Same goes to force of gravity. Displacement going to the force of gravity, it's 0. If we take it this direction, you can see that it's 270, because 270 is 0. That is why we say force of gravity and normal force, there's no work done by these two forces. Now let us look at this example. We are given that we have an object which experiences a force of 141 newtons, and then the displacement of this object is 20 meters. Now we need to calculate the work done by this force onto the object. So we start by writing our equation. Our force is 141. Our displacement is 20 cos 0. Punching this on the calculator. Joules. This is your answer. Okay, let us move to the next example. Let's say we have this particular scenario. We have two forces acting on the object. Which force applied is 30 newtons to the right. Kinetic friction is 5 newtons to the left. And the displacement of the object is 10 meters. Now the first question, we are going to calculate work done by, actually let me do this, by the force applied. Work done by the kinetic friction. So it's work is equals to the force applied, which is 30. The displacement is 10 cos 0 degrees. And then our answer should give us 300, actually it's 300 joules. Let me quickly verify this. Yes, it's 300 joules. That is the work done by the force applied. Now we look at kinetic friction. We have 5, 10. Remember the angle is 180 degrees. Why is it 180? This angle here, it's actually 180. This should give us negative 50 joules. that's it for this problem. For our next part of this lesson video, we need to understand components. We are going to relate components and the work done on an object. Now, components is a chapter which was taught in the previous classes of physics, but then I will remind you how we use these components. Now, whenever we have a force which is applied at a certain angle, which is not parallel to the displacement, that particular force has components. Now we have horizontal component, which is Fx, and vertical component, which is Fy. So basically what we do, Fx is the actual force of this. No, let me say this. Fx is the translated force of this F. So it means if we want to calculate the work done on an object whereby there is a force which is applied at a certain angle, we are not going to use that force. We are going to use the component of that force. And which component? We are going to look at the one which is parallel to the displacement. In this case, it will be Fx. As you can see, Fy is perpendicular to the displacement. It means Fy will not do any work onto the object, only Fx. Now, how do we calculate these components? Let's say we have this object experiencing a force of 200 newtons, and then this is our reference line which is parallel to the displacement. The angle between is 45 degrees. Now calculate or resolve F into components. We need to calculate the components of this F. How do we do it? The equation to calculate the horizontal component, cos theta. Then for vertical component, it's sin theta. Now these equations, they are only applicable on a flat surface. Now let us calculate. For horizontal, our F is 200 newtons. Cos, the angle is 45. Punching this on the calculator, we get 141,42 newtons. Let me quickly verify. (200 multiplied by cos 45). Yes. It's 200 sine 45. Our answer is 141,42 newtons. So this is how we calculate components of a force which is applied at a certain angle. We say it is applied diagonally. Let us look at the next example. Pause the video, work out the answers, and play the video, verify your answers. We are resolving it into components. Calculate the components, Fx and Fy. Now for Fx, 150 cos 50 answer should give you 96,42 newtons. Verifying this. Round off to 2 decimal places. Then for Fy, (114,91 newtons). I hope you got the answers. Now let us look at how we can apply this knowledge back to work, energy and power. Remember, now we are only focusing on work. Now let us look at this example. We want to calculate the work done by this particular force. Now the first thing that you need to do, we cannot use this force. Why? Because it's not parallel to the displacement, so we need to resolve it into a component which is parallel to it, which is parallel to the displacement, I mean. So we know that this is our fx, and then our fy is this direction. Now the force which we are looking for, it's the horizontal component because it's the one which is parallel to the displacement. So before we can use our equation of work, we need to resolve. Oh no, it's cos theta. (30°). Now punching this on the calculator. Our fx is 173,21 newtons. This is the force that you are going to use to calculate the work done. Now we can go to our equation. Instead of 200, we put 173,21. Our displacement is 20. Cos, now we must be careful of this angle. This angle and this one, these are two different types of angles. This angle, the red one, it's from this angle. The original force and the reference line. Or you can say the original force and the displacement. Now this one, the green one, which angle is this one? Since we managed to resolve this force into a component, what is the angle between the displacement and the resolved component? It's 0. That is the angle that we are going to use here. So we have 0 degrees. Now what is our work? It's 3464,10 joules. Now there is a way whereby we can calculate this without starting with the component. We simply put the equation of the component onto the equation of work. Now we know that Fx is equals to F cos theta, so we can simply write W is equals to, where we see F we substitute by this, displacement cos theta. Be careful of this cos theta, the angles are different. Our F is 200 cos, what is our angle again? It's 30 degrees. Displacement is 20 cos 0. Now punching this on the calculator, you will get 3464,10 joules. This is how we calculate the work done when the force is applied diagonally. So let us look at this particular problem. We have an object on top of an incline. There are a few things that we need to understand. We have our normal force, this direction. I want us to talk about normal force and gravitational force. Gravitational force, it's always vertically downwards. It doesn't matter whether the surface is an incline or a flat surface. So it's like this. This is Fg. This is normal force. Now Fg can be resolved into components. This will be our vertical. Let me make it visible. This will be our vertical component of Fg, which we represent by this symbol. And then this will be our parallel or horizontal component. I'm using tail to tail, by the way. If I'm using head to head or head to tail, it will be like this. So how do we calculate the components of force of gravity? Now, before we come to calculations, let us talk about the forces which will do work. Now you can see that normal force and vertical component of gravity will do no work onto the object because of the angle. If this is our displacement, it means the angles will be 90 degrees for both of these forces. Fg parallel will be the force which will do work onto the object. Now let us simply go through the equations. Fg perpendicular, which is our vertical. Remember, on the flat surface, our vertical component, its sign is associated with sine, the trig ratio. Now on an incline, it's a bit different. Our component, which is vertical component, will be associated with cos, And then our FG parallel will be psi. Some of the learners will say it's vice versa. Well, you are correct. So if I want to calculate the vertical component of gravity, I will use this equation. The parallel, I will use this equation. We all know that the equation of Fg is what? Mg. So where I see Fg, I can substitute by Mg. So after substituting, this equation will be Mg cos theta. Fg parallel is equals to Mg sine theta. Let us look at this example. Suppose we have this particular scenario. The question: calculate the work done on an object. The incline is frictionless, there's no friction. The object was released from the top of the inclined plane. Now we need to calculate the work done on an object. It was not pushed, there's no force applied, it's simply sliding down due to the force of gravity. Now we check how many forces does work on the object. Normal force doesn't do any work because it's perpendicular to the displacement. Now what we have the force of gravity, but not just the force of gravity, but the horizontal component of the force of gravity. So that is the force which does work on the object. The equation, we need to calculate the horizontal component of the force of gravity. This is the equation we are going to use. Now we need to find this. We know the equation. Mass is 2. Our acceleration then we should get 2 multiplied by 9.8 sine 60. From here we can calculate our work. What is our displacement? It's 10. Joules. It's very important to know how to draw a free body diagram. Remember, in vectors from the previous science lessons or classes, we do have what we call a free body diagram and force diagram. In most of the questions from the previous question papers, the common question is free body diagram. So it is very important for us to know what is a free body diagram and how to draw a free body diagram. Now suppose you have an object experiencing a force on a frictionless surface, and then we want to draw a free body diagram of this scenario. Free body diagram. An object is represented using a dot. Then we need to label actually to represent all the forces which are experienced by the object. Normal force, weight or gravitational force, and then we have our force. In this case, we don't have the kinetic friction because I said the surface is frictionless. The surface is not frictionless. How do you draw a free body diagram? Remember a dot, normal force, we have our weight, Fg, kinetic friction, this is our force. The object is being pushed, it goes up on a frictionless surface. The free body diagram, we are going to have Fg. Remember, normal force, it's always perpendicular to the surface. And then we have our force applied. The object is being released from the top of the inclined plane, sliding down, so there's no force applied. Free body diagram, we have our Fg, normal force, by the way this surface has friction, then we have Fk. It's been pushed. The surface, it's not frictionless, so there's friction. Free body diagram, normal force, force applied, there's friction, applied, Fg, normal force, Fk. The surface is not frictionless. Fg, Fk, normal force, force applied. So this is how we draw free body diagrams. Now we look at the second part of this chapter, which is energy. Now we know that energy is the capacity to do work. Some of you will say the ability to do work. Now energy, it's also associated with work. As the force is doing work onto an object, energy is also there. Now we know we have different types of energies. We have electrical energy, chemical energy. We have light energy, heat energy. We have mechanical energy, we have potential energy. We have kinetic energy, together with sound energy. Now, in this chapter, we are focusing mainly on EP, which is potential energy, and EK. We are going to talk about these two types of energies. Now, let us get to it. Kinetic energy. Kinetic energy is the energy that the object has due to its state of motion. So it simply means, in order for us to talk about kinetic energy on an object, the object must be in motion. If it's stationary, the kinetic energy is 0. Now we can prove this using the equation. Our equation to calculate kinetic energy is EK, which this EK stands for kinetic energy. Half m is the mass of an object, and then v is the velocity of its object. No, is the velocity of the object, I mean. Now, in order for us to calculate the kinetic energy of an object, we need the mass of the object and the velocity. Potential energy. The energy of an object it has due to its position. So this one is based on the position of the object. As you can see, the equation, m is the mass of an object, g is 9,8, our acceleration, and then h is the height above the ground. So potential energy and kinetic energy, you must know the difference. You should be able to calculate using the two equations. Now, these two equations, or these two energies, how are they related to the work energy? actually not work energy, how are they related to work? Now look at this equation. Work net, the net work experienced by an object, it's equals to its change in kinetic. So when we expand this equation further, we have half mv f squared minus half mvi squared. So basically this equation simply means all the work done on an object, it's equals to the mass of the object, its final velocity, minus the mass of the object, its initial velocity. Please write this equation down, it's very important. And then what do we call this equation? We call it work energy theorem. This is basically the work energy theorem. How do we define work energy theorem? We do have acceptable definitions and laws provided in the exam guideline. But in general language, work energy theorem is work done on an object which is equals to the change in its kinetic energy. So you can see the change is final minus initial. Work net, we look at all the forces acting on the object. We look at all the forces which does work on the object, and then work net is the sum of all the forces. Work net is the sum of all the work done by the forces on the object. It's equals to its change in kinetic energy. I hope it makes sense. We have another energy which is mechanical energy. Now this is the equation. Emech stands for mechanical energy. It's equals to half mv squared plus mgh. The sum of the potential energy, which is EP, and EK, it's equals to Emech. Also write this equation down. Very important. Conservation of mechanical energy. Mechanical energy before, it's equals to mechanical energy after. Now this is our equation. This is EK plus EP. It's equals to EK plus EP. Write this equation down, it's also very important. Now let us look at this scenario. We are given that the scenario, the height of the building is 45.92 meters, and then we have point A. We also have point B. Point B, the height is 25.51 meters. Now the question, calculate the speed at point B. Now the ball was released. How do we do this? We need to use the conservation of mechanical energy. We consider this position as before, and then B as after. So we can use this equation, EK plus EP is equals to EK plus EP, whereby here we consider this as before, this is after. Now before, as you can see that the ball was released, so it means our velocity is 0 at point A. And then you're looking at the velocity at point B. Furthermore, when we expand this, we have mgh half mv squared plus mgh. Now I forgot to state that the mass of the object is 50 kg. So half, the mass is 50. Remember, this part is for point A. Now what is the velocity at point A? It's 0. Plus the mass, we have 50, 9,8. What is our initial height? We have 45,92. Equals to half, the mass is still 50, v, we are looking for v, so it's v squared, plus the mass is 50, 9,8, and then the height will be at point B. What is the height? 25,51. Now we can see that this 0 multiplied by the other terms will simply be 0, and then we can solve for this v. So we are going to punch this on a calculator. Now this should give us 22500,8. It's equals to, this will be 25 v squared, and then we can see that what can you do? Okay, we punch this on a calculator. 25,51 plus 12499,9. From here we're going to transpose this to the other side. So we have 25 v squared, it's equals to 225,008, 8 minus 12499,9. Then we simply divide both sides by 25. So this will result into 1 multiplied by v squared is v squared, is equals to 22,500 minus 12499,9 all over 25. We simply square root both sides. And then v is equals to, we simply punch this on a calculator. Square root of 225,008 minus 12499,9 all over 25. So answer is 20 meters per second. Remember, when we are calculating for the speed, we don't need to write the direction. Remember, speed is a scalar quantity, so we simply calculate the magnitude. That's it for this problem. We are still looking at energy. Let us look at this problem. Now let's say the first question is saying calculate the maximum potential energy at A. Now we must know that at position A, the object, by the way, this is a pendulum. The object is stationary, so it means the velocity is 0. Now we don't have to use conservation of mechanical energy. We simply need to calculate the energy due to the position of the object. So we are going to calculate potential energy. Now the energy that we need the mass of the object, we need the gravity, which is the acceleration, we need the height. So we are given the mass as 800 grams. Before we can substitute, we need to convert these grams into kg. There is a lesson video whereby we talk about unit conversion. So from grams to kilograms, we simply multiply by 10 to the power 3. Actually, we multiply by 10 to the power -3, or we divide by 1000. So 800 grams divided by 1000, we have 0.8. Then our gravity is 9.8. Our height, we need to convert 50 centimeter to meters. So how do we convert? We simply divide by 100, or we multiply by 10 to the power -2. Then we simply punch this on a calculator. 0.8, 9.8, 0.5. Our answer is 3.92 joules. So this is the energy at A. Now the next question, calculate the velocity of the object at its lowest point or lowest swing, that is point B. This is the lowest point. Now we want the velocity. Now remember, energy cannot be destroyed or created. So at point B, we do have the energy. What is the magnitude of the energy? It's 3.92. So we can use this equation. EK is equals to half mv squared. Our EK, it's this. So we have 3.92. Our mass is 0.8 v squared. So energy was transformed from one form to another, from potential energy to kinetic energy. Now, to make this simpler, I can simply write 0.5, 0.8 v squared. I divide both sides by 0.5, 0.8, 0.5, 0.8. Then this will result into 1 multiplied by v squared, it's v squared, it's equals to 3.92 all over 0.5, 0.8. Then I simply square both sides. I end up having v is equals to square root of 3.92, 0.5, 0.8. Then I simply punch this on a calculator. 3.92, 0.5, 0.8. Velocity is 3.13 meters per second. To the right, this is the final answer for this question. Now here's a situation whereby it goes with questions. Now it's simply based on work, energy and power. We need to use all the pre-knowledge that we have to try and answer these questions. Now the scenario is saying Jane pushes a small cart of mass 5 kg with a speed of 1 meters per second. she suddenly increases the force acting on the cart to move at 2 meters per second for a distance of 50 meters. Now the first question is saying calculate the initial kinetic energy. Now we need to check what do we have. We can see we have the mass, which is very good. We have the initial velocity, we have the final velocity. We have enough information to answer the first question. Now the first step that we are going to do, we are going to write the equation. That is initial. Half, and then our mass is in kg, it's fine. Our initial velocity is 1 squared. So we can see that EK is equals to 2,5 joules. We are done with number 1. If you have confidence that you can answer these questions, feel free to pause the video and try to work out the answers. Now let us go to number 2. Number 2, we should calculate the final kinetic energy. So it's EK is equals to half mv squared, which is final. Half 50, and then the velocity from 1 meters per second to 2 meters per second squared. We punch this on the calculator, so we have 0.5 50 2 squared oh no, there's a problem. The mass is not 50, but it's 5. So our answer is 10 joules. Done for this one. We go to number 3. Number 3 is saying the work on the cart. We need to calculate the work done on the cart. So we need to use work energy theorem. Is equals to change in EK. It's work net. So we have half mv squared final minus half mv initial, it's initial squared. So work net is equals to half. No, we already have the initial and final kinetic energy, so we can simply take our previous answers. So we have 10, that is the final, minus 2,5. So work net is equals to 7,5 joules. This is the answer to number 3. Number 4. Question number 4 says the force causing the cart to speed up. Now we are looking for the force. You can use this equation. Work is equals to now we have our work, which is 7,5. We are looking for the force, and then the displacement from the scenario, it's 50 meters. So we have 50 cos 0. Now basically we have 50 force, it's equals to 7,5. We divide both sides by 50. This will result into 1 multiplied by F, it's F, and then 7,5 divided by 50. So our force is 0.15 newtons. This is number 4. Number 5, the acceleration of the cut. So we simply use Newton's law. So we have 0.15 is equals to the mass, it's 5, then A. We divide both sides by 5. This will result into 1. 1 multiplied by A, it's simply A. It's equals to 0.5 divided by 5. The answer should give you 0.1. No, there's a problem. It's 0.15 divided by 5. Okay, the answer is 0.03 meters per second squared. Now you can see how we apply the knowledge we have of work energy so far. This is how the questions will be examined. You should be able to be versatile with each and every question. Conservative force is the next part of the lesson we are going to look at. What is conservative force? Conservative force is a force for which the work done in a moving object between 2 points is independent of the path taken. For example, gravitational force, the elastic force in a spring, and electrostatic force. Now let us explain this furthermore. Now we all know that gravitational force, whether the object is going up or down, the direction of the gravitational force will always be downwards. So it's independent of the path taken by the object. Whether the object goes up or down, the gravitational force will always point downwards. So we say gravitational force, it's one of the conservative force. We always have an opposite of anything in this world. Now the opposite of conservative force is a non-conservative force. Non-conservative force is a force for which the work done in a moving object between 2 points depend on the path taken. For example, frictional force, air resistance, tension in a cord. Now we all know that frictional force depends on the motion of the object. When the object goes to the right, frictional force will be in the opposite direction. Now if the object changes direction, frictional force will also change direction. So we classify frictional force as one of the non-conservative forces. This is one of the equations we use in work, energy, and power. It's based on conservatives and non-conservatives. So work done by non-conservative forces, it's equals to change in EK plus change in EP. When we expand this equation, this is the equation we have. Write it down, is one of the most important equations. Now the last part of the chapter is power. Now what is power? Power is the rate at which work is done. Now we all know that the moment you hear the word rate, simply means it's anything over change in time. Rate of velocity is change in velocity over change in time. Rate at which work is done, it means the equation for power is P, it's equals to work over change in time. If you can calculate the work done on an object, work done on an object by a particular force, and then you have time taken for that force to do work on that object. We can use this equation to calculate power. Now write this equation down. We do have another equation. Let's say we have a force acting on an object, and then the object is moving at a constant speed, which is the average velocity, and then we want to calculate the average power. We use this equation. Now this is the end of this lesson video. Remember, this is lesson 1 of work, energy and power, whereby we look at the basics, we go through examples, we explain each and every concept. Now there is lesson video number 2 of the very same chapter, whereby we look mainly at question papers. All the equations that were given in this lesson video, they are going to be applicable when looking at the actual questions from the question papers. This is Bahula SJ. Thank you very much.